Thank you very much, Rector Sadovnici, for your very kind introduction. It's such an honor to be back at Moscow State University, and a pleasure as I have spent so many very happy weeks and months here over the past, 4 or 5 decades, a very long period of time. 1.3 billion years ago, here on Earth, multicelled life was just beginning to spread around the globe. But in a galaxy far, far away, 2 black holes circled around and around each other. And may I have the visuals on the screen? Thank you. These are what the 2 black holes would have looked like to your eyes if you had been there watching them move. The black spots are shadows of the black holes against a field of stars far away, and the shadows make this swirling pattern due to a phenomenon called gravitational lensing. And as these black holes went around each other, they emitted gravitational waves, ripples in the fabric of space and time, a huge crash of gravitational waves as the black holes collided and merged. These waves traveled outward from the galaxy in which the black holes lived. They traveled into the great reaches of intergalactic space, and for 1.3 billion years, these gravitational waves traveled across intergalactic space until 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. The gravitational waves reached the outer edges of our Milky Way galaxy. For 50,000 years, they traveled across our galaxy, reaching the Earth on the 14th of September in 2015. They arrived first at the tip of the Antarctic Peninsula, near the South Pole. They traveled up through the Earth, not affected at all by the matter of the Earth, and emerged in Livingston, Louisiana, in North America, at what we call LIGO, the Laser Interferometer Gravitational Wave Detector. 7 1,000ths of a second later, 7 milliseconds, they emerged through the Earth at Hanford, Washington, where we have a second LIGO detector. The gravitational waves moved the detector in a manner I will describe later, creating a signal that went into a computer, and then the data from the computer were analyzed by a team of 1,000 scientists around the world. This is just a small portion of the scientists, for about 5 months. And finally, the team agreed, yes, this was definitely a gravitational wave burst that we have seen, human beings' first encounter with a gravitational wave. And the discovery was announced on the 12th of February in 2016, and it made the front pages of all the major newspapers around the world. So how did we get here? I'm going to talk for a short time about the birth of LIGO, the strange birth of LIGO a long time ago as a mega project. The story begins with Albert Einstein. In 1916, Albert Einstein used his theory of general relativity, which was at that time was less than 1 year old, to predict the existence of gravitational waves. And he told us that a gravitational wave is something that stretches and squeezes space. And so anything that is lying at rest in space, let's say out far away from the Earth where there is no other gravity, it rides on the space and gets pushed back and forth, different things. So here what I have is a bunch of particles that are all at rest out in space. And when the gravitational wave comes, they are moved together and apart. Apart in this direction, together in that direction, then apart and together in the manner that is described. Einstein predicted these waves, but when looking at the strength of the waves, he said, in effect, that these waves will be so weak that humans will probably never ever discover them. Well, in the 1960s, approximately 50 years later, Joseph Weber at the University of Maryland in North America was the first scientist to attempt to discover gravitational waves experimentally. He built a gravitational wave detector, and he had the courage to do this because of major changes that had happened since Einstein. First, Einstein had not known about black holes or neutron stars, but these are ideal sources of gravitational waves. So we had new sources, he had new possibilities for stronger waves than Einstein thought could exist. Second, we had new technology, lasers, computers, which could be used to build more sophisticated gravitational wave detectors than Einstein ever conceived of. In the meantime, in 1966, I had been inspired about gravitational waves by Weber and by Einstein. So I arrived as a new professor at Caltech in Pasadena, California, and I created a theory group working on the theory of black holes, the theory of neutron stars, and the theory of gravitational waves. In 1968, I made my first visit to Moscow State University, and there I met Vladimir Borisovich Brzezinski. We became very close friends, and I discovered that he was the only other person in the world who was working to build gravitational wave detectors. He here and Joe Weber in the United States. In 1969, Weber announced that he was seeing evidence for gravitational waves, and this was a great discovery if it was correct. 1972, Brzezinski here at Moscow University, together with his colleagues, had built a gravitational wave detector similar to Weber's. They did this very quickly because Brzezinski was already working on other kinds of designs, so he was prepared to move quickly. And they were the first group to go in and search for the waves that Weber thought he was seeing, and the answer was no. They saw no such waves. So there was a great mystery, and then over the next several years, other experimental groups in the West built such detectors, and they also saw nothing. Also in 1972, I was beginning to realize as a theorist that if gravitational waves could be discovered, then they would be a wonderful tool for exploring the universe. And I wrote my first technical paper with a student, William Press, developing a vision for what gravitational wave astronomy would be. Let me explain part of that vision. It's interesting to compare the electromagnetic waves with which astronomers have normally observed the universe with the gravitational waves that we propose to use to observe the universe. Electromagnetic waves are oscillations of electric and magnetic fields that propagate through space as time passes. Whereas gravitational waves are oscillations of the very fabric, the shape of space-time itself. Electromagnetic waves are, in astronomy, an incoherent superposition of emission from individual particles or atoms or molecules, whereas gravitational waves are emitted coherently by the bulk motion of large amounts of matter or mass or energy. Electromagnetic waves are very easily absorbed and scattered by matter, by dust typically, between us and the source. Gravitational waves are never significantly absorbed or scattered, not when they travel through the Earth, and not even in the very early era of the universe, near the Planck era when our universe was born. And so gravitational waves are ideal for exploring things like the birth of the universe. These two types of waves are so different that it seemed obvious to me and my colleagues that many sources of gravitational waves would never be seen with electromagnetic waves, with light, X-rays, radio waves. And indeed, that is the case. We have not seen any electromagnetic waves from colliding black holes, but we have seen gravitational waves. On the other hand, there would be sources of waves, we believed, where you have both electromagnetic and gravitational waves. You can use them together to learn about the universe, and that has also come to pass, as I will describe later. The other implication was that because these waves are so different, electromagnetic and gravitational, there would be huge surprises come from gravitational astronomy. Again in 1972, this was a very special year, Rainer Weiss at MIT invented a new kind of gravitational wave detector called a laser interferometer gravitational wave detector. He proposed that you hang from overhead supports, as I show down here on the right side, 4 mirrors, and they are hanging and free to swing. And when a gravitational wave comes by, The mirrors along one arm in that configuration are pushed apart. Along the other, they're pushed together, then pushed apart here and pushed together on the other arm. And he proposed to use a laser beam through a technique called interferometry to measure those changes between the two arms. The remarkable thing about his proposal was not just that he had this idea, but that he then went in and he identified all of the major sources of noise that you would have to face in this experiment. He described how to deal with each source of noise, and he then computed what sensitivity these instruments could achieve. He compared with the strength of the waves that I and my colleagues were predicting, and said, if you make this instrument a few kilometers in size, you will have a good possibility of success. And that was a remarkable technical paper that he wrote describing this. Interestingly, and really quite important, 10 years earlier, the same idea for this kind of detector was invented here in Moscow by two students of Moscow State University, Mikhail Gerstenstein and Vladislav Pustovoit, 1962. The difference was that they were theorists. Weiss was an experimenter. Weiss knew how to compute, how to identify all the noise sources, how to compute the sensitivity that could achieve, how to deal with the noise sources. Gerstenstein and Pustovoit did not. And the big lesson of this is the communication between theorists and experimenters is tremendously important. If they had been talking to very good experimenters at that time, if they could get the attention of very good experimenters, things might have moved forward here, but that didn't happen. Vladimir Brzezinski was a friend of theirs, but he wasn't yet working in the field, working on this subject, and did not get into this subject until later. When I heard about this idea for a gravitational wave detector, it was while I was finishing writing a textbook on gravitation, on Einstein's relativity theory. And I had not yet studied this idea in detail, but it was obvious to me that this would never succeed. And so in the textbook, I wrote that it is not promising. I was very conservative in what I wrote. I didn't say it will never succeed, but that's what I believed. And why did I believe that? What was required for success is to monitor the motion of those mirrors to enormous precision. If you take 1 centimeter, you divide by 100, you get the thickness of a human hair. I don't have a human, I have one down here. You get the thickness of a human hair. Divide by 100, again, you get the wavelength of the light that is used in these gravitational wave detectors. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 1,000 again, you get the strengths of the gravitational waves, the motions of the mirrors that you would expect to have if your detector is a few kilometers in size. It was obvious to me that this could never be done. And so I basically said that. And then I studied Weiss's paper, his 1972 paper, in depth. I had conversations with Weiss and with Brzezinski, and after about 3 years of this, I became convinced that this could succeed, and that we should create at Caltech a group working in gravitational wave experiment. And so, of course, what I wanted to do was bring Brzezinski from Moscow State University to Caltech to lead our effort. Brzezinski said no. He did not want to leave Moscow State University. He declined to move, but he became our advisor, our most important advisor on this project. And so instead we brought Ronald Drever, a superb experimenter from Glasgow University, to Caltech to start our effort. From 1980 to 83, under Drever's oversight, the Caltech team then built a gravity wave detector of Weiss's type with 40-meter long distance between the mirrors. We needed a distance 100 times bigger than that, we thought, for success. So this was a 1% of the size that was required. In the meantime, at MIT, Weiss and his group finished a smaller prototype detector and carried out a feasibility study for detectors of the very big size that we believed was needed. Then in 1984, we at Caltech and Weiss at MIT joined together to create the LIGO project. And it was led initially by Weiss, by Drever, and by me. We were the most terrible leaders that science has ever seen for a big project. We could not agree on what we wanted to do. We could not agree on how to do it. And so there was, for 3 years, we just accomplished almost nothing until we really were told, and it became obvious, you have to have a single director for a mega project like this was going to be, a single director who has the ultimate responsibility and authority for making decisions. He will make those decisions in consultation with a large team, but one person is the final leader. And so we brought in a man named Robbie Vogt, who had been the first chief scientist at the Jet Propulsion Laboratory. It's a Caltech facility which does all of the unmanned space missions, at least the unmanned spacecraft missions in the United States. And he then came on board in 1987, and under his leadership, we developed a proposal to design and construct LIGO gravitational wave detectors, a proposal we sent to the U.S. National Science Foundation. We said we would first build the facilities, a large vacuum system and several large buildings in which the gravity wave detectors would live. And then we would have a two-step strategy for our detectors. We would build a first set of gravity wave detectors, or interferometers we called them, and they would be simple enough that we knew we could build them successfully, but not accurate enough for us to be able to see gravitational waves. We would probably see nothing. And then we would have to build a second set of interferometers, the advanced interferometers, which would ultimately have success. It was very hard to get approval to spend what at that time was $300 million to build detectors that would not succeed. Particularly when the astronomers would tell the government, if you give this to us to build optical telescopes, we will see wonderful things immediately. And so it required 2 years to get approval from National Science Foundation and from Congress to move forward. But we were very wise in explaining that this was hard. It was so hard we would have to do it in 2 steps, because that is in fact what happened. We brought on then a new director, Barry Barish, who really knew how to lead a project like that and organize it. And from 94 to 99, he led us in the construction of the facilities. And in 1997, he said to us, there's no way that you at Caltech and MIT can have a large enough team for success, because these instruments are so complex that they require a much bigger team. And so we will open this up to institutions across the world. And so he did. He created the LIGO Scientific Collaboration, which now has 1,200 scientists in approximately 90 institutions in 18 nations. He then also led us in the construction of the initial interferometers, and then he was stolen away by the high-energy physics community to lead the design for the next generation of large colliders for high-energy physics. And so we then brought on a succession of 2 other great directors, Jay Marks and David Wrightsey. But at any time, we needed a superb director to organize everything and make this happen successfully. In 2010 to 2015, we installed the advanced interferometers, which had been designed based on what we learned with the initial interferometers. But before I tell you what happened next, I want to back up and explain the contributions from Russia. Brzezinski's group at Moscow State University have been absolutely crucial for the advanced LIGO detectors. We have here with us today Mitrofanov and Khalili from that group. Channing's out of town, and there are several others, and they have just been crucial contributors. Here is some of the things that they did. I won't read through them. What I want to highlight is the fact that Brzezinski told us in 1968 that whatever kind of gravity wave detector you try to build, to have success, you will ultimately have to measure the motion of large masses so accurately that they will behave like an electron inside an atom. They will fluctuate about where they are randomly due to quantum effects, so-called quantum fluctuations. And he said you will have to develop a new kind of technology to control these quantum fluctuations of your masses. In LIGO, it's these mirrors at the ends of the laser beam. And the centers of mass of these mirrors are the things that fluctuate, and they fluctuate by amounts large enough that they can hide the gravitational waves you're trying to find. And so Brzezinski said you must develop then quantum non-demolition technology, a new kind of technology to deal with these fluctuations. Elsewhere at the Institute of Applied Physics, the group of Alexander Sergeyev has been developing instrumentation to handle high laser power for other purposes, but also for LIGO. And in particular, the Faraday isolators they have developed, which are crucial pieces of the instrumentation, have been brought into LIGO and have been playing a crucial role in the advanced LIGO gravitational wave detectors. Contributions from computational physicists have also been important. In fact, I got very worried in the early 2000s that we did not know how, computational physicists did not know how to simulate two black holes going around each other and colliding. And we had to have those simulations because when you see the waves, you must compare the shape of the waves as measured by LIGO with the predicted shapes in order to understand what it is the source is doing. And nobody in 2001 could take two black holes and evolve them on a computer even through one orbit around each other, much less all the way down as they spiral together and collide. And so I left LIGO in 2001. LIGO's success is not due to me, it's due to the younger generation of scientists working on LIGO. I left in order to start an effort in the computational physics here. Just as I didn't build the instrumentation for LIGO, I didn't write the computer codes either for the computations. However, I provided the direction that we ought to be going in the scientific motivation and the extraction of scientific information from the simulations. And by 2015, when the advanced detectors were just beginning to operate, we had successful simulations in our group in collaboration with Cornell University and in several other groups around the world. September 14, 2015, the first gravitational wave search with the advanced detectors was planned to begin in about 3 days. The detectors were being tuned, they were being prepared to begin the search, and in the middle of the night, after everybody had gone home to sleep for a few hours, a gravitational wave burst came in. And the next day, when the computers showed the gravitational wave signal, the director of LIGO, Dave Reitze, he announced to the team, we have started the first search. It began 3 days early because we saw something. And it was really a rather remarkable thing. The signal was so strong, and much stronger than we expected, that it could be seen by your eyes in the instruments of the two different sites in Livingston, Louisiana, and Hanford, Washington, the same signal. When the signal was cleaned up, the oscillations, I plot upwards the stretch of the distance between mirrors and down the squeeze together. The oscillations in this so-called gravitational waveform, when cleaned up, are like in the gray there, and the red is the numerical relativity predictions. But the predictions depend on the masses of the black holes and also, to a lesser extent, on their spins and how far away they are. And so it is by comparing with those simulations that we concluded that we had two black holes 29 times as heavy as the sun and 36 times as heavy as the sun. They had collided and merged and produced a final black hole 62 times heavier than the sun. 3 solar masses were gone into gravitational waves. It is as though you had taken 3 suns, completely annihilated them, and put all of the energy that came from annihilating these suns into gravitational waves. And these gravitational waves then propagated out across the universe and ultimately to LIGO for LIGO's gravitational wave detection. And we also concluded the source was 1.3 billion light years away. In LIGO, we have now seen 6 colliding black holes. And this shows the gravitational wave shapes for 5 of them. By the time the 6th one came along, the detections were being sufficiently routine that my colleague who made this slide didn't even put the 6th one on there. So we were seeing beginning to see lots of gravitational waves, each with a different set of masses and spins and different distance from the Earth, but beginning to study the behavior of warped space-time when black holes collide. It was crucial to know where the sources were on the sky so we could look for light, X-rays, radio waves, look for electromagnetic waves. And so here I show you the measured error boxes on where the sources were on the sky for several of these gravitational wave sources, I guess for 4 of them, and then a 5th one down in the corner. Those error boxes are very, very big. It's very hard to search them because it's such a big region on the sky. We needed to know much better than that on the sky where the source was to tell the electromagnetic astronomers where to look. Fortunately, in August of last year, a new gravitational wave detector came online, the Virgo Detector, that's near Pisa, Italy. It's a detector that is built and operated by a set of scientists from France, Italy, the Netherlands, Poland, and Hungary. And the way in which we determine where the source is on the sky is by the delay in arrival of some feature in the signal at 3 different locations on the Earth. So we triangulate by the time delay in the arrival of the signal. We had to have 3 in order to say in a small error box where it was. Once we had 3, then on the signal that came in on August 14, these are the names of the signals, GW for gravitational waves, 17 is the year, 2017, 8 is August, and 14 is the day. The signal that came in on August 14, 2017, the error box is very small compared to the others because we now had an additional detector. So these multiple detectors are crucial. Just 3 days later, we had another gravitational wave signal, and it turns out that it was coming from something that I'm showing you a simulation of here, not 2 black holes, but 2 neutron stars. Each of these neutron stars, each of these stars has a density in its center that is 10 times higher than the density of the nucleus of an atom. It has a mass of about 1.5 times the mass of the sun and a diameter of about 20 kilometers. So think 1.5 suns compressed into 20 kilometers. It's almost a black hole. And according to theoretical simulations, as these 2 stars go around each other, they emit gravitational waves, they spiral together, they collide, and they produce a gigantic fireball of exploding ultra-hot nuclear matter traveling outward into interstellar space. That fireball explosion has been named a kilonova by the theorists who predicted such explosions. And we saw one with LIGO. This is 170817, so it's August 17th of last year. The gravitational wave signal is shown here. What I'm plotting now is a little different from what I showed you before. Time is plotted horizontally, and you can't see very well the time scale, I think. It's -6 seconds, 0 seconds when the signal goes rising up very fast in the end, and then 6 more seconds to the right. So that's frequency of oscillation of the waves. So the stars go around each other faster and faster as they get closer together. The waves oscillate faster and faster at higher and higher frequencies. And then at the collision, that occurs at time 0 in this plot. 1.7 seconds after the collision, this fireball was expanding. It was so dense at first that no light or radio waves or any electromagnetic waves could get out. But after 1.7 seconds, it became thin enough, transparent enough that gamma rays could get out. And there was a strong burst of gamma rays, as shown here, as seen by the Fermi Gamma Ray Telescope in orbit above the Earth. 1.7 second delay. Then we could look on the sky and say, where were the gravitational waves? They were the small dark green region, according to LIGO and the new Virgo detector. And where were the gamma rays coming from? That was the dark blue region. They had even worse angular resolution on the sky than we had. Then the astronomers kept looking, because we had sent, in LIGO, had sent out an alert to all the world's astronomers. We've seen something, go look. And they were waiting and watching. And over the next several hours, first X-rays were seen, then ultraviolet radiation, then optical, then infrared, then radio waves. This became the most studied event in the history of astronomy. About 20% of the world's astronomers observed it during that first 24 hours with all kinds of telescopes. We call this multi-messenger astronomy. Light, radio waves, X-rays, gravitational waves. We think of those as messengers that bring us information. By comparing the electromagnetic waves with theory, a rather remarkable verification was made. The prediction had been made earlier by the astrophysicists who simulate colliding neutron stars, that neutron stars collisions is the place where most, perhaps all of the gold and platinum and other precious metals in our universe are made, in these collisions of these stars. Well, the gravitational waves told us here was a collision. The electromagnetic observations told us, looking at the details, yes, gold and platinum, heavy metals were made there. A very great verification of this prediction. So this is an example of what can come by combining gravitational and electromagnetic observations. So these observations gravitationally were made with 3 detectors, the 2 LIGO detectors in North America and the Virgo detector in Italy. Somehow this got displaced into Africa, but it's supposed to be up there in Italy. I apologize. I apologize to the Italians. In 2020, approximately, a new gravitational wave detector called CAGRA will begin to operate in Japan. At about 2022, a 3rd LIGO detector will begin to operate in India. The detector itself was a duplicate of the LIGO detectors in the US, but the facilities are being built by the Indians, and they will assemble the detector with help from the LIGO team in North America, and then they will operate the detector. And why do we want these additional detectors? They improve our accuracy to see where the source of the waves is on the sky. So if we have only LIGO and Virgo, the error boxes we saw before are long and thin. You don't know where the wave is with very good accuracy. Just as soon as LIGO India comes on board, then the error boxes get squeezed down, much smaller north-south, and CAGRA reduces the size east-west. And so we will be able, with this network now, then, of 5 gravitational wave detectors, to say with much better accuracy, where should the electromagnetic astronomers look? I'm going to show you 3 photographs of the advanced LIGO detectors. This is, you've seen this before, this is what the detector looks like from an airplane with the arms. These are vacuum pipes down which the laser beams shoot between the mirrors that hang from overhead support. 4-kilometer long vacuum pipes. Here on the inside you see the vacuum chambers in which reside the mirrors that hang from overhead supports and other instrumentation. And Barry Barish, our great leader who really organized LIGO and made it happen, he likes to put an American baseball player there just to show you the size. Why he didn't put a LIGO scientist there, I don't know. It's his form of humor, I think. And then here is a photograph of one LIGO mirror hanging from an overhead support by a fused silica fiber. And the technology for that suspension, which is absolutely crucial, was developed here at Moscow State University by a team of Brzezinski, Mitrofanov, who's here in the audience today. And that technology in the depths of the Cold War was transferred from Moscow State University to the West. When everybody was worrying about technology being transferred from the West to the East, we were very quietly accepting Moscow State University technology to make LIGO a success. And I thank you, Valery, very much. The LIGO instruments are very complex. They have about 100,000 data channels. 100,000 data channels that tell you what's going on inside the instruments and in the environment. Why so many? Because in order to do what I thought was impossible, to measure these very, very small motions, it was necessary to have instruments that have many, many different components in the interior, any one of which could misbehave. And so you need to have a monitor of everything that could go wrong. And so when you turn on a gravity wave detector this complex, it's similar to Victor Frankenstein, who built his creature and only learned the creature's personality after the creature was brought to life. You only learn the personality of the instruments after the instruments are turned on, and then you have to carefully, much more carefully than the Victor Frankenstein did, you have to very carefully do experiments to learn its personality, and then coax it toward the personality you want, coax it toward design sensitivity. We expect to be at design sensitivity by 2020, and at that time we will see approximately three times farther into the universe than we are seeing now. That means we will see a volume of the universe 3 cubed or 27 times higher than we now see. That means instead of seeing about 1 black hole collision per month when the instruments are operating, we will see about 1 a day. And just imagine that. Every day you have a pair of black hole collisions because you're seeing so much farther. And what will we see with this instruments? Will we expect to see not just colliding black holes like I described, but also spinning neutron stars, so-called pulsars, gravitational waves from pulsars. We expect to watch black holes tear neutron stars apart. We've already seen neutron stars collide. We expect, but this will be very rare, but we expect to see the cores of supernova explosions, the birth of a neutron star when the core of a star collapses and then creates a neutron star, and then there's an explosion called the supernova. And there will be enormous surprises, I am quite sure. And so this gives you some sense of what we think we're going to see. Advanced LIGO in 2020, 2021 is not the end. By the late 2020s, it is possible, we have now tentative plans for an improvement on those current detectors called Voyager or LIGO 3, in which we should see many collisions of black holes per day. And by the 2030s, something called Cosmic Explorer in the United States, something called the Einstein Telescope in Europe, which should see every black hole collision in the entire history of the universe. All the way back, going all the way back, everything that arrives at Earth, the signals that arrive at Earth from black hole collisions, going all the way back to the earliest moments of the universe, for black holes less heavy than 300 suns. And that's not all. LIGO looks at gravitational waves that oscillate with periods of milliseconds. But we will, by the 2030s, have operating a gravitational wave detector in space that is being prepared by the European Space Agency called LISA, 3 spacecraft that track each other with laser beams, that looks at gravitational waves with periods of minutes to hours. And by the sometime in the 2020s, a technique called pulsar timing arrays, which I will not describe, should be seeing gravitational waves with periods from years to decades. Another technique that I will not describe in detail called Cmb Polarization. I expect by sometime in the 2020s we'll see definitively but indirectly, gravitational waves with periods of hundreds of millions of years. Now, of course, that's longer than a graduate student lifetime. And so what you will actually do is you see a pattern of polarization of microwaves on the sky that is produced by gravitational waves from the birth of the universe with this kind of a period. I'm going to finish by describing some of the science that we expect to extract from our gravitational wave detectors. First, explorations of black holes, and then exploration of the birth of the universe. These are the things, we'll see many other things, we'll do much other science. I've given you the example of colliding neutron stars. But these are the things that make me most excited, exploring black holes observationally and exploring the birth of the universe. So, according to Einstein, to general relativity, a black hole is made not from matter like you and I, but instead is made from warped or curved space-time. But you can visualize a black hole in the way I am here. You imagine taking the black hole, it's like a flattened sphere. You take an equatorial slice through the black hole, a surface that cuts right through the equatorial plane of the black hole. The geometry of that surface is not like a flat sheet of paper. It is not Euclidean. Rather, it is strongly warped, curved, by the huge energy that makes up the mass of the black hole. And so if you take that surface and you embed it in a flat higher dimensional space, which is sometimes called the bulk or hyperspace, this is what it would look like. It looks like a funnel. So far away is where we are on Earth, but when you're near the black hole, that surface goes down. So what that means is as you near the surface of the black hole, the horizon at the bottom of this diagram, as you go in, the circumference of circles around the black hole stops decreasing. You keep going in, but the circumference doesn't change. So it becomes like that on a cylinder. The color coding shows the slowing of time near the black hole. Where it is yellow, time is flowing at about 10% of the rate that it is back on Earth. And the white shows the dragging of space into whirling motion, so-called dragging of inertial frames by the spin of the black hole. And this is a depiction then of all the features of this warped space-time of a fast-spinning black hole. Now, if we have a small black hole orbiting around a large black hole, I'm going to slip forward through the slide and show you what this orbit looks like if I remove the warping of space. The orbit is very complicated. It does not look like the orbit of the Earth around the sun. It's not elliptical. It's made very complicated by the warping of space, by the peculiar strength of gravity, and by the dragging of space into whirling motion. That orbit, as the small black hole explores the entire space around the big black hole as it goes around and around and around. And over a period of, say, a year, you may get 100,000 orbits. So a very complicated gravitational waveform that in fact carries a full map of the warped space of the big black hole that's being explored by the little black hole as it travels around. So the LISA mission, which has just the right frequency band to study this, will be used to map the space-time geometry of big black holes the same way as space programs have mapped the surface of Venus using radar, or the surface of Mars optically and with other kinds of radiation. So mapping big black holes just like we map the surfaces of planets. And what if the central body is not a black hole? I'll give you an example of what's called a Manco-Novikov naked singularity. so down here at the center, there's not a black hole. We don't see it, but there's what's called a naked singularity, a place where gravity is so strong that general relativity fails, but it's a particular solution of Einstein's equations that describes this. And this brown orbit near the naked singularity turns out to be mathematically chaotic in the mathematical sense of the words, whereas the orbits farther away are nice and smooth and predictable. And so the map that you would extract from the gravitational waves produced by an object in that brown orbit would be very, very different from the map that you get of a black hole. So we can use this with Lisa to search for strange kinds of massive objects around which small black holes or compact small white dwarfs or other compact bodies orbit. Then the one other thing about exploring black holes that I'm very excited about is exploring the dynamics of space-time geometry. And we do this by computer simulations and comparing with gravitational wave observations. And I'm going to give you the example of the first gravitational wave signal that LIGO saw, GW 150914, September 14th, 2015. And the team, so-called SXS computer simulation team that Saul Tukolsky at Cornell and I at Caltech organized, created the simulation that was compared with the observations that I showed you earlier on, and to see then just what were the properties of the black holes that produced this burst. And then our team went back, and 3 graduate students in the team at Cornell, they built then a picture from the simulations of what the space-time geometry was doing during this collision. So you see these 2 black holes. They are funnels, as I showed you for the shape of a black hole before. The color coding red is where time is slowed enormously. The collision is going to occur soon, so I've slowed down the movie. And right at the collision, I'll stop the movie momentarily. A huge splash in the shape of space, and an oscillation, and the gravitational waves go traveling off. That is what really happened in the collision. You can only understand it by looking in from a higher dimension and seeing the oscillations of the shape of space. The power output during this collision, when space is splashing up like the surface of the ocean in a storm, the power output, the energy per unit time, was 50 times larger than the total power of all the stars in the universe put together. 50 universe luminosities coming from one object, a black hole binary, 2 black holes colliding, for a very short time, for a few 1/100ths of a second. But that was enough, 50 universe luminosities and a few 1/100ths of a second to send off 3 solar masses of energy in gravitational waves. But this is by far the most powerful explosion we have ever seen evidence of in terms of power, except the Big Bang in which the universe was born. And so let me then turn to the birth of the universe at the end of my talk, and the birth of the fundamental forces of nature. I told you earlier that black holes are by far the most penetrating form of radiation, the only form of radiation that could be created in the birth of the universe and travel without being absorbed or scattered by matter to Earth to bring us a picture of the birth of the universe. But first, let me tell you about the prospects to observe not the birth of the universe, but the birth of the fundamental forces that control the universe, that govern what goes on in the universe. Theory predicts that the universe is born very hot, and that in the extremely early universe, the electromagnetic force did not exist. There was no such thing as an electric field, no such thing as a magnetic field. But there was something called the electroweak force. And as the universe expanded and cooled, when it was about 10 to the minus 12 seconds old, 1/1,000,000th of a second old, there was a phase transition, similar to the conversion of water vapor into water droplets. A phase transition in which the electromagnetic force was born and the electroweak force ceased to be relevant. And this birth of the electromagnetic force very possibly occurred inside what is called a first-order phase transition. I have to assume that that's the case for what I'm going to say. If that's the case, then the electromagnetic force was born inside droplets, like water droplets condensing from water vapor. And these droplets inside the electromagnetic force existed. Outside, there was no electromagnetic force. But by contrast with water droplets, these droplets had enormous pressure in them, and they expanded at enormous speed, nearly the speed of light. They collided, and as they collided, they produced a strong burst of stochastic, rather random gravitational waves, but with a particular spectrum associated with this process. These gravitational waves had very short wavelength. This was a very high energy process. But then the universe expanded for 13 billion years. And the wavelength of the waves expanded, and today these waves are predicted to be in the right frequency domain, the right wavelength domain for LISA. So with LISA, we will look for the stochastic random gravitational waves with a particular spectrum produced in the collision of these bubbles in which the electromagnetic force was born. And I think this is just wonderful to have the prospect to watch, to verify observationally the birth of the electromagnetic force. Even more exciting is to observe the birth of the universe. So theory says that our universe came into being, space and time came into being along with the universe in what is called the Planck era, because it's created by the combination of general relativity, which is Einstein, and quantum physics, which is Max Planck. The unification gives us the laws of quantum gravity, and those laws of quantum gravity govern the birth of the universe. And according to theory, and there is considerable observational evidence that this is true, in the first 10 to the minus 33 seconds of the life of the universe, you have to imagine 0 point, and what is it, 32 zeros in 1 second. There was an extremely rapid expansion of the universe called inflation. And it was Leonid Petrovich Grishchuk, a close friend of mine here in Moscow, who in 1975 also trained as a student here at Moscow State University. 1975, he predicted that that if there was anything like inflation, that whatever gravitational waves were created in the birth of the universe, they would be amplified enormously and become very, very strong by this rapid expansion of the universe. And so he predicted primordial gravitational waves. And subsequent work by others has argued strongly that in fact what came off the Planck era at the very beginning is only the minimum amount of gravitational waves that the laws of quantum physics allow, so-called vacuum fluctuations of gravitational waves. But the predictions are that these vacuum fluctuations would be so amplified by inflation that they would be strong enough to be seen today. And there are two techniques by which I expect them to be seen in the coming decades. First, this Cmb polarization technique that I haven't told you the details of in the 2020s. And by about the 2050s, a LISA-type space mission called Big Bang Observer may see them. Very different frequency bands, extremely different frequency bands. And what we will learn from those observations, we will learn a combination of information about the birth of the universe and inflation. And because the birth of the universe is controlled by the laws of quantum gravity, these will be crucial observational data to tell us about the laws of quantum gravity. And I look forward to, I hope to still be alive, I may not be, but I look forward to the possibility, perhaps the likelihood, that what is seen will be different than the theorists are predicting, because we've got the wrong understanding of the laws of quantum gravity. And that will be tremendously exciting to have the possibility to test these laws in this way. So let me just conclude by saying it's 400 years ago since Galileo built his first little optical telescope and turned it on the sky and discovered the 4 biggest moons of Jupiter. And it is 3 years ago that LIGO advanced detectors were turned on and discovered gravitational waves from colliding black holes. Now, in the 400 years since Galileo, electromagnetic astronomy, with light first, then radio waves, X-rays, gamma rays, and so forth, has completely changed our understanding of the universe, a complete revolution. Our understanding of the universe bears little resemblance to Galileo's. Because of 400 years of electromagnetic astronomy, I invite you to speculate about what gravitational astronomy, together with electromagnetic astronomy, crucial observations with telescopes around the world, what that combination will bring us over the next 400 years. Thank you.
Мы все находимся под колоссальным впечатлением блестящей лекции профессора Торна. Вот можно сказать, что это одна из лучших лекций, которая звучала в этом актовом зале. Господин Торн, мы восхищены тем, что вы рассказали, и поражает, что вы не только рассказали о достигнутом, вы наметили еще план того, что ученые будут делать. И чего достигнут, может где-то разочаруются, но впереди очень интересная картина, путь познания мира. Спасибо. Я навсегда запомню вот эту нашу встречу, нашу лекцию. Спасибо вам. Уважаемые коллеги, сегодня у нас открытие фестиваля науки через очень короткое время. Поэтому мы поступили следующим образом. Был сайт, и вы задавали вопросы. Мы отобрали всего несколько вопросов, потому что невозможно, чтобы были сотни вопросов, это бы заняло еще полдня. И вот, господин Торн, позвольте вот несколько вопросов огласить, которые задали сидящие в зале, но по сайту при подготовке лекции. Итак, первый вопрос, я читаю. Гравитационные волны, которые впервые зафиксировали в ЛИГО, долетели до Земли больше миллиарда лет. Летели. Чтобы их поймать, понадобилось 50 лет усердной работы. 50 лет в масштабах человеческой жизни – очень существенный отрезок времени. В масштабах Вселенной – это ничтожный отрезок. Как вы ощущаете время? Такой вопрос.
Well, it is a peculiar thing that astronomers have to think about time in billions of years and sort of perceive it through some knowledge of the processes that occur in stars and galaxies over billions of years. But the reason at the beginning of the talk I described what was happening on Earth when these waves were launched is because to me it is just phenomenal that they started when there was only multicell life beginning to form. They reached our galaxy when the Neanderthals were here, and they reached us today. For me, this flow of time and this story is just phenomenal. On a more personal note, let me just say that 50 years of working on one project, that's a long time. So as a theorist, I worked on a few other things at the same time. When things were quiet, I tried to work on the theory of time machines, for example. But the work on this project, and I think on any project that you really love, and this is crucial, that if you're going to do something hard, you had better love it. It was so much fun, and so enjoyable, and had so many different pieces of physics involved that the time seemed to pass quite quickly, and that we never got bored. Thank you.
Спасибо. Произошел большой взрыв. Образовалась наша Вселенная. А что было до? Могли ли быть другие большие взрывы и образовывались другие Вселенные?
I don't know. However, when we fully understand the laws of quantum gravity, we will be able to ask this question more wisely, and we may be able to start getting real answers. And that is part of my message of this, that we have a possibility through gravitational wave observations to actually observe the birth of the universe, to learn about the laws of quantum gravity, and to contribute to being able, in the middle part of this century perhaps, to answer these questions.
Ну, мы уже говорили, что профессор Торн не только блестящий ученый, но и выдающий популяризатор науки. И вопрос, видимо, связан с этим. Уважаемый профессор, вся разумная жизнь, которая фигурирует в научной фантастике, более или менее напоминает людей. А вот если бы вас попросили придумать для фильма планету, на которой существует разумная жизнь, какими бы вы представили людей, тех, кто населяет эту планету?
So I did get involved in that question when I was working on the movie Interstellar. The movie went through several phases, but the first 3 drafts of the screenplay were done by Jonathan Nolan. And in those drafts, Jonathan, or Jonah, he imagined a form of life that is actually based on what we learned from evolutionary biologists and other kinds of biologists, is a possibility, patterned on some forms of life that you would see in tiny ponds in Antarctica, but forms of life that are hierarchical, in which small, simple entities come together to make things that are more and more complex, much like in computer simulations. And so we had a wonderful piece of the story that involved this kind of life. And when Jonathan's brother, Christopher Nolan, took over the film, he removed that, so it's gone. But that's my experience with it.
Спасибо. Дорогие коллеги, Кип Стивен Торн является почетным доктором Московского университета. Но ученый совет, отмечая выдающийся вклад, присуждает вам, уважаемый господин Торн, диплом как Нобелевскому лауреату по случаю посещения Московского государственного университета имени Ломоносова, выступления с лекцией в актовом зале. Позвольте вручить вам такую.
It is absolutely beautiful.
Господин Торн, сюрприз. Можно сейчас я вот вам подарю. Вот смотрите, в этом журнале, в этой подшивке собрана вся история посещения господина Торна Московского университета. Начинается с того, что в 1979 году профессор Брагинский представил господина Торна к званию почетный доктор Московского университета. Затем решение ученого совета Московского университета, выступление на нем Владимира Борисовича Брагинского, декана факультета Фурсова, и вся та ваше выступление в том же 1981 году. Это история вашего пребывания в Московском университете. И мы нашли несколько фотографий тех лет. Не знаю, имеются ли они у вас. Здесь Джозеф Вебер, Кип Торн, Том Тойсон, Владимир Брагинский.
Wonderful. Absolutely wonderful. Thank you. Thank you so very much.
Дорогие ребята, давайте стоя поаплодируем профессору.